In this video, I will explain the concept of non-deterministic finite automata. In short, it can be called as NFA. So first we'll see what is non-determinism. So earlier we discussed about deterministic finite automata. So now we'll see what is non-deterministic finite automata. So in the finite automata, we already know that if there is a state and when we give some input, then it moves from one state to another state. So like this. So in this example, if you see here, so there is some state Q and there is some state P. If I give some input, it is going from Q to P. So if there is only one state or at most one state, it is deterministic. So that means we know what is the next state. If there are more than one state like this, so let's say this is R. In this case, it is going from Q to P and Q to R. So for the same input, let's say the input is A and input is A. So for the same input, it is going from one state to uh, two states. So then it is called non-deterministic. So when, for example, if we give some input, let's say something like A, A, B, A, B something. So when the automata reads the symbol A and it is in state Q, then we are not sure about to which state it should move next, right? So either Q to P or Q to R. So that means we cannot determine. Okay, we are not sure about the next state. So in that case, we'll call it as non-deterministic finite automata. So, and in other words, we can say that it can exist in one or more states. It can exist in more than one state. Here, it can exist in more than one state. Then it is called non-deterministic finite automata. So there is one example here. So for input 1 from Qi, so the current state is Qi, let's say current state is Qi for input 1 and 1 here. So it is going to Qi and Qk. So that means it is going to more than one state. So we say that it is uh, non-deterministic. We cannot determine the next state. Right. This is the formal definition of non-deterministic finite automata. So it is also represented by phi tuple, like DFA. It is also represented by phi tuple. There will be a set of states, and there will be input alphabet, and there will be start state, and there will be set of final states. And the difference is in the transition function. For DFA and for NFA, the difference is in the transition function. Right. So I'll write both things here. Here the transition function is defined by Q by sigma implies subset of Q. That means any subset of or you can say it as power set 2 power q. Power set of q is uh, power set of q is 2 power q. That means when you give an input on particular states, let's say if you take the previous example, you take state q and give an input 1, it may go to any subset of states here. So earlier it was uh, qi to qk, something like this. So that means this is a subset, okay, subset of q. So that's why we map it from q by sigma to 2 power q. So it may go to one state or two states or three states or any number of states of q. Now what is that DFA? DFA, the transition function is q by sigma implies q. That means it will go to only one state in q. It will go to only one state in q. Whereas in NFA, it may go to any subset of 2 power q. Any subset of 2 power q. So if you write uh, the set and subset, then you'll understand better. So let's say there are two states pq, then 2 power q will have 4 states. So it can be empty state, it can be p, it can be q, it can be pq. So in DFA it will go to either p or q. In NFA it can go to either empty set, or it can go to p, or it can go to q, or it can go to both p and q. So the non-determinism comes here. So it may go to the next state can be p and q. So so this is a difference between DFA and NFA. So to understand this exactly, you need to have a basic idea of sets and subsets. Yeah, so this is defined by the 5 tuple. So only difference between NFA and DFA is in the transition function delta. So this is a transition function delta. You can write like this, delta. Here also the transition function delta. Delta is a function. So we call it as transition function. So a function maps one input to another input. Okay, so function maps from one input to another input. So one set to another set. Sometimes it may be same set also. Here also the function takes two inputs. It will take two arguments. One is state and another one is input. So when it takes state and input, it will go to either one state or set of states based on whether it is deterministic or non-deterministic. How to use an NFA, right? So it is similar to DFA. Again, there is no difference. So these are language recognizers like DFA and NFA. These are language recognizers. So what is language? Language is set of words. Okay, language is set of or sentence is language set of words. So set of sentences becomes a language, right? So now we'll come to the level of words. Okay, so we'll consider words here, and if a word in some language, so let's say W belongs to some language L, and the set of words W are accepted by this NFA, then we say that this language is accepted by NFA. So if you take this example, what is the input here? Input is a W in sigma star. So sigma is here the alphabet. Okay, sigma is alphabet. Sigma star is all possible words of that language. For example, if sigma is if sigma is a comma b, so this will contain all possible, sigma star will contain all possible strings. So it can contains empty string, it contains a, it contains b, a b, a b, a b, a b, a b, a b, like this it goes on forever. It will include all possible strings of a b, all possible length. Okay, so it contains strings of length 0, 1, 2, 3, 4, and any order of a's and b's. And when we take the string w, and this NFA reads the string. Okay, so if you place the input on a tape, this finite control will read the strings of this symbols of this string one by one, and moves from one state to another state. It moves from other state, one state to another state. So after reading this, after reading all the symbols of this string here, let's say there are 5 symbols. So after reading the 5 symbols, after consuming the 5 symbols, okay, if it is in the final state, okay, then we say that this uh, string is accepted by, or the word is accepted by the NFA. Okay, so it is similar to DFA. There is not much change. Only difference is you have to follow all possible next states. Okay, you have to follow all possible next states. That means in NFA we know that uh, for some state, from some state, for some input, it can go to multiple states. Okay, more than one state. Let's say here for the input 1, it is going to state P R. So when you check whether this is accepted, when you check a string W is accepted by NFA or not, what you have to do is, so when it is going from one state to multiple states, you have to check, consider all possible paths. Okay, so if by following one path, it may go to accepted state or final state. By following one another path, it may not go to accepted state. Okay, so that's why we should consider all possible states. Okay, all possible paths. So if you take the real-time example, you are in some place. Okay, you are in some place and you want to go to some other place. So there can be multiple paths. There can be multiple paths, but there will be some paths where you will reach the dead end. Okay, so these some paths we may not reach. Some paths we may not reach. Through some paths we can reach. So in this case there are 3 paths from this point. So these 2 paths, uh, in these 2 paths we reach the dead end, but whereas the other path we reach the destination. So in a when it comes to NFA, as there can be multiple paths, because multiple transitions are there, it will lead to multiple paths. So then we need to consider all possible paths. If at least one path is successful, that means if after consuming all the strings, all the letters, symbols of the string W, if you are in final state for at least one path, then that string is acceptable. Right. So this is NFA for strings containing 0, 1. So that means the string should contain 0, 1. You take any string, it should contain 0, 1. So we need to construct an NFA which recognizes this language. So the regular expression is given here. That means 0 plus 1 whole star. So it means it contains all possible strings of zeros and ones. So including epsilon, that means empty string. And after that 0, 1 should be there. And then after that it can be any string of zeros and ones. Okay. So in the middle or in the beginning or at any position, it should have 0, 1 as a substring. Okay, so if you see this example, so the corresponding NFA for this language or this regular expression is given here. So in Q0, the input can be either 0 or 1, because this language, the alphabet is 0 1. So it is given here, the alphabet is 0 1 and the start state is Q0. So in the beginning, the input can be 0 or 1. So here the self loop with 0 and 1, it represents the this part. It represents this part, 0 plus 1 whole star. So this is represented by this state Q0 with self loop 0 1. So that means you can read 0 and stay in the same state. You can read 1 and stay in the same state. You can read 0 and same state. So likewise, you can read zeros and ones as many as you want. And when you encounter this 0 1, so in this string 0 1, first input symbol is 0. So in that case, you move from Q0 to Q1. That means you have consumed this 0. Okay, the finite automata consumed 1 0 of this string. Okay, because we want this 0 1. So once you encounter this particular 0, so there will be multiple zeros here, but when you encounter this 0, you need to move from Q0 to Q1. That means you have consumed 0. That means in this state Q1, what is how do you define this state? In this state, the finite automata consumed 0 of the string 0 1. 0 1 substring, from the 0 1 substring we have it has consumed 0, and then the input is 1. That means 0 followed by 1. That means we will enter the final state Q1, sorry, Q2. So when we reach Q2, after that you can read any string, or it can read any string of zeros and ones. So it can read 0, it can read 1 0 1, or empty string. Okay, so this final state Q2 is represented by this. Q2 is for this substring. So this is Q0 and this is Q2. And here 0 1, when we reach when the finite automata reads Q0, sorry, 0 1, it moves from Q0 to Q2. So if it reads this 0, it moves from Q0 to Q1. If it reads this 1, then it moves from Q1 to Q2. Right. So now once you draw this state diagram, as the NFA is represented by uh, 5 tuple, so which contains Q, that is set of states. So now Q is a set of states which contains Q0, Q1, Q2, 3 states, and sigma is we already know 0 1, and start state is Q0, and final state is Q2. There is only one final state, Q2, and the transition table. So this transition function delta is represented by the transition table. Okay, right. So how do you write this transition table? So this transition table contains a set of rows and columns. The rows represents the states, and the columns represent the input symbols. As we have only two input symbols, there are two columns, and there are three states. There will be three rows, and the entries, the entries of this table, like there are 6 entries, so we need to compute what are the entries. So these are the next states. Okay, so what is transition function? Transition function maps from one state to another state based on the input, right? So what is the destination, or the, if you take this mapping, here it is Q, and this codomain is 2 power Q. So this is domain and this is codomain. So we'll map from Q to 2 power Q. Now, so that's why the entries of this table should be subset of this 2 power q. Okay, so if you see here q naught on 0, if you see the diagram, q naught on 0, it can go to either q naught or q1. So there are two transitions for the input 0. Okay, so now that means there are more than one state, so it is represented by a set. Okay, so flower brackets are there, q naught q1, so it is a set now. So it is going to multiple states, and q naught on 1, it is going to the same state q naught, right? Next, when we go to q1, so q1 on input 1, it is going to q2. Q1 on input 0 is not there, so it is empty set. And q2, so q2 on 0 or 1, it will be in the same state. So q2 on 0, q2, and q2 on 1, q2, right? So this is a transition table which represents the transition function. So transition function can be represented by this table. So let's briefly discuss about transition table and transition function and state table. So this is state diagram. So this is the state diagram. So a finite automata can be represented using a state table or state diagram. So this is the state diagram. State diagram is a graph. Okay, state diagram is a graph. This state transition table is a table. Okay, it is a tabular representation. There are two notations for representing the finite automata. One is transition table and another one is state diagram. So state diagram is a graph, and graph means there will be nodes and edges. So for every state there should be a node. Okay, so here there are three states and three nodes are there, q0, q1, q2. And edges, so are transition. Okay, transition means moving from one state to some other state including same state. So these edges represents the transition, okay, from one state to another state. So here if you see here q0 on input 0, it is going to q1. So this edge is represented by the edge represents the transition, and each edge should be labeled. So labeled with the input symbols. So this edge is labeled 0 comma 1 because for both inputs it is going to same state. Here q2, uh, it has self loop, and this edge is denoted by this edge has the input symbols 0 comma 1. So for these two inputs it is going to the same state. So this is a graphical representation of the finite automata, and this is a tabular representation of the finite automata. So where the rows contains the states and the column contains the input symbols. So both represents this finite automata. You can represent the finite automata with a phi tuple, and you can represent this finite automata with a state diagram or state table. We can call this as a state table or transition table because overall it represents the transition. Okay, transitions of the states. It can be represented as state table or transition. So transition means moving from one place to another place, whereas this one is state diagram. Okay, so state diagram is it is a graph which contains nodes and edges. Graph contains nodes and edges. Nodes are states are represented by nodes, edges are represented by edges represent the transitions, state nodes represents the states, right? So this is about transition table and transition uh, state diagram. Now there is one state called special state called dead state. So sometimes we don't represent dead states. Okay, so if you want it, we can explicitly represent. Uh, if you see this example, so we this finite automata or automata theory has applications in right. So this finite automata is used in various applications like pattern recognition, search engines, right, in compilers and all. So where it can recognize some, one example is recognizing some words. Okay, so if the keyword is like in this example while, so we all know about while loop. Okay, so this is automata which recognize this the string while, right. So we want to recognize this string while or word while. So other than anything, it should go to a dead state, because we want to read only the string while. Okay, so the first letter to be read is W, then H, then I, then L, then E. So it should follow the same sequence WHILE. In case instead of on state Q naught, instead of W, it gets some other input symbol, it will go to dead state. If it gets uh, any other symbol on Q1 other than H, it will go to dead state. So we want only these symbols from these respective states. Other than that, we'll get an error. So we go to the final, sorry, dead state. Okay. So, and the NFA for the same purpose is here. Okay. So transitions into a dead states are implicit. So that means even though it is not mentioned the dead state here, so it is implicit. Implicitly, uh, it is conveying that any other symbol will lead to a dead state. So in general, we consider only the uh, input symbols that leads to the final state in NFA. Whereas in DFA, we'll take all possible symbols and will include generally dead state also if it required. So it is not required every time. If it required, we'll explicitly mention the dead state.